Next speaker, Professor Hanci Chi. Topic of his talking is the existence and non-existence of cohomogeneity one Einstein matrix. Please, yes.
Thank you. Dobrý den. Jmenuji se Hanci Chi. Já z Xi'an 交通六部 Universidadu. It is my great pleasure to be invited to this wonderful online conference. And I feel like I have a special bond with the countries of Ukraine, especially the cities of Lviv, because my wife, she studied music at Lviv, and I have been there for a couple of times. And yeah, it is my great pleasure to share some of my recent research with you. That is the existence and non-existence of Einstein metrics of cohomogeneity 1. So first of all, let's have some definitions. I suppose everyone here is familiar enough with the ideas of Einstein metrics. And we would like to focus on Riemannian metrics today. So the definition is if you have a Riemannian metric, and if its Ricci curvature is a constant multiples of the metric itself, then we call the metric an Einstein metric. So generally, it is very difficult to have an explicit solution of Einstein metric because it's a set of second-order nonlinear PDEs. So it's in general very difficult to solve. And for very long periods of time, that the Einstein metrics that people know are homogeneous. That is, you assume that the manifold is homogeneous, and you have a lot of symmetry, and in that way, the PDE got reduced to a set of algebraic equations. And you will get some interesting examples out of it. And so it's a natural question to ask whether you can have inhomogeneous Einstein metric. Well, some people would like to apply, special holonomies, such as the very famous Calabi-Yau manifold, many great works, done by Aubin, Xintong Yao, Tian. But today we would like to focus another way to construct inhomogeneous Einstein metrics. That is, you use the conditions of cohomogeneity 1. So here's the second definition. So what does it mean by being homogeneity 1? Well, it means that the manifold is being isometrically acted on by some Lie group G. And in that way, the principal orbit, G mod K, is of codimension 1. So you can think of the cohomogeneity 1 manifold as the some kinds of next case to the homogeneous manifold. So it still has a lot of symmetry, but it leaves you with the one-dimensional orbit space. So you can parameterize the orbit space, and the PDEs got reduced to a set of ODEs. And that way, we hope that we can generate more examples of Einstein metrics. Right, so here's the more explicit formulation. Generally, so the T here, it parameterizes the one-dimensional orbit space. And for each T, you will have a homogeneous metric that is defined on the principal orbit. And of course, you need to consider the initial conditions and the terminal conditions for the homogeneous metrics on the principal orbits to collapse. Sometimes you might have one end. So in that case, you might have a non-compact manifold. And some other times, for example, that for the talk today, we will consider a case where the homogeneous metrics collapse on two ends to the singular orbits. So the manifold is compact. Right. And there are many works that have been done on the cohomogeneity 1 Einstein metric. In fact, the first examples of inhomogeneous compact Einstein metric is of cohomogeneity 1. And it's related to the physics, and people call them the gravitational instanton. So it's a positive Einstein metric that is defined on by gluing two copies of CP2 together. And it's done in 1978-ish. And after that, Barabajuri generalized the page metrics to in a more systematic way. So you can replace the hypersurface with the circle bundle over a Fano manifold. So in his work, you don't necessarily have the base space to be homogeneous. You just need the Kähler-Einstein base, and then you consider the circle bundles of it, and you can still reduce the Einstein equation to a set of ODEs. But of course, his works include the cohomogeneity one manifolds. Right, and later on, done by Page and Pope, Koiso, Sakane, and Jun Wang and Mackenzie Wang. So all these people, they have been constructing new cohomogeneity one Einstein metrics. And a common feature shared by these metrics are the principal orbit or the hypersurface. They are circle bundle over either a Kähler-Einstein manifold or a product of Kähler-Einstein manifold. So later on, in 1998, done by Christoph Byrne, he considered a new case. That is, if you replace the circle bundle over, if you replace the circle bundle with a S3 bundle over a quaternionic projective space, right? Then you can still try to get the cohomogeneity one Einstein ansatz. And also in his work, he also construct many non-standard Einstein metrics on low-dimensional sphere, right? And later on, by his work have been further generalized or brought to many other cases, such as those done by Lorenzo Frascolo, Mark Haskins, Jan Nienhaus, and Matthias Wink. And the last one, as you can see in the last line, is the recent generalizations of Byrne's metrics to the higher dimensional case. So we are going to, talk more specific, give a more specific descriptions on that. So in the manifold, it's a something called a double disk bundle, right? So recall that we replaced the circle bundle with a S3 bundle over HPN, right? So that's the quaternionic Hopf vibration. So if you more specifically choose the group triple GHK as shown in here, so you can look at the principal, the GMA K is actually a total space of a S3 bundle over HPM. And furthermore, if you look at the isotropy representation, it actually got split into two irreducible summands. So one is 3-dimension and the other one is 4M dimension. So every homogeneous, G invariant matrix on GMA K looks like this, like with some background metric Q, right? So you can control the G invariant metric using two factors, right? F1 and F2, right? And put it into the in the stories of cohomogeneity one metrics, you can think of F1 and F2 as functions that are defined on the orbit space, and we consider the ODE systems that is related to F1 and F2. Right. So this is a more more straightforward illustration, right? So the double disk bundle, it has the topological structure looks something like this. It's like gluing two copies of disk bundle over the principal orbit, which is a 4M plus 3-dimensional sphere, right? And on two ends, the principal orbit collapse, right? It collapses to the singular orbit, which is HPM. So if you consider the cohomogeneity one equation on this compact manifold, you will have a initial condition, that is how the fiber grows out from the singular orbit. And on the other hand, you need to consider how the fiber collapses on the other end. So very naturally, for this manifold, you have this Z2 symmetry. That means you can flip it with respect to the principal orbit that is in the middle, right? So you can apply the symmetry and make some argument. So you can imagine that the local solutions on this end is pretty much the same as the local solutions on the other end. And the question boils down to how you can bridge these two local solutions in the middle, right? Right, so that's the story that I have just introduced. So in general, if you have a group triple, right, we can generalize this idea to many other principal orbit. So in general, if you have a homogeneous vibration where AGMA K is a homogeneous sphere, and furthermore, if you can control the principal orbit using two quantities, using two factors, F1 and F2, then you can write down the general, cohomogeneity one Einstein equation with respect to this particular principal orbit. And of course, each G mod K will be related to a structural triple, D1, D2, and a constant A, where D1 is the dimensions of the fiber, the spherical fiber, and D2 is the dimensions of the base space. And and we have the similar picture, right? So in the middle, you have principal orbit, and on both ends, it collapses to the singular orbits. Right, but I haven't told you what is the constant A. Right, so as you can see, right, according to the work done by Eschenburg and Wang, so they give a very systematic way to study the initial problems of the cohomogeneity one Einstein equation. So using that formulation, you can write down the ODE fairly easily, and you can see there's a constant capital A right here. So it actually comes from the square norms of the O'Neill tensor in the theories of Riemannian submersion. So if capital A equals to 0, it more or less tells you that the base space is integrable, so that the principal orbit is necessarily a Riemannian product. But in general, if you give me any principal orbit G mod K, right, like constant A, usually it's larger than 0, so it's a constant. And of course, the ODE looks a little bit complicated, but it's actually packed with geometric meanings. So if you look at the left-hand side of the ODEs, right, you have the derivative of the principal curvature of the principal orbit. And you can write down the derivatives of the principal curvature as the first derivative term, as you can see here, which is the D1 plus D2 thing. That's actually the mean curvatures of the principal orbit. And those terms without derivative, they are actually the Ricci curvature of the principal orbit. So using the theories of Riemannian submersion, right, you can write the Ricci curvatures of the cohomogeneity one space in terms of the intrinsic geometry and extrinsic geometry quantity on the principal orbit. So that's the equations. Right, and of course, then the last term here, the last lines of the ODE, you have some kinds of conservation law. So the second order derivative can actually be canceled out. Okay. Right. So how do we approach to such a ODE system? Well, fortunately, we have some hint. That is, if you give me a principal orbit with capital A being 0, like I said, right, the principal orbit is a product between the fiber and the base space, then you have a trivial solution for the Einstein equation, right? That is simply you just take the product space. You let F1 to be sine function and F2 to be a constant, right? Then automatically you have a product Einstein matrix on a product space. That's some kinds of trivial solution, right? But the question is, can we make A little bit larger, right? If you give me a D1 and D2, if you give me a dimension pairs, right? Can we enlarge A little bit larger than 0, so we can have some criteria to check, right? If if A passes through some threshold, then the existence statements holds, right? On the other hand, if the quantity capital A gets too large, right, you can actually argue that the AGMA K with such a large A does not admit any G invariant Einstein metrics within the two Solomons ansatz, right? So, and therefore the natural question will be asked, like, if you can decrease A little bit from this blue rectangle over there, right? So you can have like non-existent statement, for more cases of principal orbits, right? So that's the mindset behind before we do any analysis. Right, and it turns out that indeed, right, we succeeded in finding these two numbers. One is called chi d1 d2, and the other one is psi d1 d2. More that is, like, we enlarge the numbers of A, and we to some numbers, right? Give me any d1 d2. Like, the formula for chi is a little bit too complicated to be fitted in one slide, but you can always let the computer do the jobs, right? You throw in d1, d2, and it will throws out a number chi, and you can check if A is smaller than chi. And once A is smaller than chi, then that particular principal orbit shall admit a cohomogeneity 1 Einstein matrix on the associate double disk bundle. Right, and for the number of psi, the formula is actually quite simple compared to the chi, right? And here the small n is just the dimensions of the principal orbit, so it is just d1 plus d2. Right, so every principal orbit, right, with d1, d2a, such that a is larger than or equal to psi, shall not give you any cohomogeneity 1 Einstein metric with respect to that particular ansatz, right? Right, so in that way, with this theorem established, then we can generate many inhomogeneous Einstein metrics from the works that is on the homogeneous Einstein metrics, right? So I'll show you a bunch of new examples, and all these examples are obtained from the homogeneous spaces that is done, in all these work listed in here. So I will not name them one by one, but perhaps the most commonly used one is the classification paper done by Dickinson and Kerr, and also very recently done by Laurit and Will. They also generate two interesting examples, and I will talk more about it in a more specific way. So here's the list, the first list, part one. So if you take the AGMA K as the principal orbit, then we have a inhomogeneous Einstein matrix on the associate double disk bundle. Also, you can think of the double disk bundle as a 3-sphere bundle over the singular orbit, right? They are topologically equivalent. And as you can see, each of these group triple, the isotropy representation, it's split into two irreducible summands. And a common feature shared by these principal orbit is the fiber, the spherical fiber, is always of dimension 2. And the base space is always dimension 4m. Which is something called the Wolf space, because they emit quaternionic Kähler structure. So yeah, they are actually, like, these set of principal orbits, they are actually the twistor bundle over a quaternionic Kähler symmetric space. And we, according to our theorem, we know that taking these as the principal orbit, you will have an inhomogeneous Einstein matrix on the associate double disk bundle. And the second class of the example is listed in here. As you can see, the group G does not have to be simple, right? You can take G as some non-simple Lie group. And the first example that we have here is actually the Ledger-Obata space. So the isotropy representation of the first example listed in here, they're actually equivalent, but it does not bring too much obstacles to our analysis. We can still, consider the cohomogeneity one system and construct the examples on the products of sphere S4 cross S3, right? Because the principal orbit is S3 cross S3. It is also worth mentioning that although the principal orbit is a product of two spheres, the product is in the sense of topology, right? It is not a Riemannian product. In other words, the Riemannian metric is not a product of two, of two metrics on S4 and S3. Yet the topological structure is a product. Right, and the other two examples listed in here, they are the right. The base space are non-symmetric, strongly isotropically reducible space. Okay, so in the last two cases, so for the second one, SP2 mod SP1 is actually a Berger space, seven-dimensional Berger space, and also the last space there, you need to have the SP1 to be the maximal one embedded in G2. But anyway, like for these two cases, you can still compute the number, the constant capital A, and we can check that capital A is smaller than chi. Therefore, the homogeneity one Einstein metric exists. And finally, I would like to emphasize that our result is not limited to those principal orbit that are of two Solomon type, that are of two Solomon, right? Sometimes a principal orbit, the isotropy representation can split into more than two Solomons. But if you can, consider a ansatz by imposing some of the quantity to be equal, you can still obtain a two Solomon ansatz. Like for example, in the first line here, right? It is also a twistor space. It is a twistor bundle over a Wolf space, but the isotropy representation got split into three isotropy Solomons, and you have two Solomons that is controlling the singular orbit. But for this case, we can still make the whole singular orbit to be controlled by one single factor. So it is of two Solomon type, but it is not of two Solomons, right? And we can still consider the principal orbit with a group structural triple as 2, 4m, and capital A, and we can check that A is small enough to generate a new example of cohomogeneity one Einstein metrics. Right, and the second example here, it's something called the I believe that they call it the generalized Wallach space. Once again, the singular orbit is controlled by two factors. It's split into two irreducible Solomons, but you can still make them equal. You can impose the conditions that they are controlled by one single factor. And we realize that for higher dimension, right, once you bring the dimensions to be large enough, you can still generate new examples out of it. And for the last three examples, the singular orbit, it's a product of two singular orbit that has been mentioned before, right? For the third example, it is just a product of two copies of HPM. And for the second last case, the singular orbit is two copies of Berger space. And the last case is just two copies of G2 mod the maximal SP1. Right, so for all these principal orbits, right, by checking a very simple relatively simple inequality, you can immediately obtain the some homogeneous Einstein metrics, which is great. Right, so now I would like to discuss how we tackle the ODE system. So like this part might be a little bit more technical. So yeah, the way that we did it is to, first of all, we apply a coordinate change so that we can compactify the phase space on both ends. Right? Recall that we have two ends for the singular orbits. So if you make the following coordinate change and define the following functions, then the second order ODE system can be transformed to a first order ODE systems. So as you can see, x1 and x2, they are more or less tells you how large is the are those principal curvature, and the function y and z, they are just quantity without derivative, right? So in that way, we have this new ODE system with 4 variables, right? So the prime is taken as the derivative with respect to the eta instead of t. So one of the advantage of this new ODE system is that it's polynomials on the right-hand side, right? What is even better is that the initial condition and the terminal conditions, they are transformed to critical points of the vector fields on the right-hand side. Right, and of course, we have a conservation law for this ODE system. That is a algebraic surface described in here. So in total, right, the phase space is actually of 3 dimensions. Right, you have 4 variables, and with the conservation law, so you have a 3-dimensional dynamical system, right? So like I said, right, so using this coordinate, the whole system actually got compactified, and the initial condition is transformed to the critical points P0 plus, and the terminal condition is transformed to the another critical points, that is P0 minus, right? And everything is happening between h equals to -1 and h equals to +1. So let me remind you, what is h? So h here, it more or less tells you the size of the mean curvature. And you can easily prove that the new system is invariant in the region where h is between -1 and 1. Right, so we want to consider the integral curves that flows out from the P0 plus, and we will hope that some of these integral curves are actually heterocline that joins P0 minus and P0 plus. And like I said, right, the phase space is 3-dimensional. So this is a projections to the x1 and x2 space. So you still have that one extra dimension from either is from y or from z. Right. And we realize that it is a common feature shared by many, shared by most of the principal orbit, that you have a very obvious solution, which is denoted as the capital phi here. So here phi, if I let z x1 to be x2, z to be mu2 y, where mu is one of the solutions from r1 minus r2 equals 0. So this yellow straight line here, it actually has geometric meaning. So it represents a sine cone over a homogeneous metric that is defined on G mod K. So recall that if you have G mod K to be a amid some homogeneous Einstein metric, then you can immediately construct a sine cone over it so that the sine cone is Einstein. So of course, it's of cohomogeneity 1, right? As you can see here, R1 minus R2 equals 0 is basically asking the Ricci curvature for the principal orbit to be the same, right? And R1 and R2, they are polynomials of degree 2, homogeneous polynomial. So if you let R1 equals R2, you will have a ratio mu2 that is from Z divided by Y, right? And we realized that, well, I mean, in Christoph Bern's work, right, like he realized that the integral curves that flows out from P0 plus is actually winding around the capital Phi, right? And with much enough winding, you can actually use the continuous argument to show that the heterocline that joins P0 plus and minus actually exist. And notice that our dynamical system is symmetric with respect to the sign of x1, x2, right? So whatever is happening for for integral curves that comes out from the P0 plus, it's pretty similar to whatever is happening near the critical points P0 minus. Right. I'll give you perhaps a three-dimensional picture for illustration. Right. So if you think of an extra dimension, like given by the variable y, then you can think of there are layers of h that represent the mean curvatures of the principal orbit. Right. It goes to 0 first, and then it decreases to -1. Right. And furthermore, right, and you have this integral curves comes out from the P0 plus that is winding around the capital Phi. And it's a very standard analytic result that there exists a continuous one parameter family of local solution around the critical point P0 plus. So it begs the questions of, right, whether, among these one continuous, interval, whether you can have some of the particular parameter that give you the heterocline, right? Right. Like I said, if you can show that, well, I mean, by the symmetry, right? If you can show that for some parameter, the integral curves passes through the point in the middle where x1 equals to x2 equals to 0, then immediately by the symmetry, you have a heterocline, so victory. And it kind of indicates that instead of focus on the whole x1, x2 plane, we can only focus just half of it, right? So here's something that we are going to do. So we are going to apply some global analysis. The way that we, tackle this ODE is we introduce the following functions, right? And the derivatives of these functions, they kind of like cooperate with each other so that, the level set of these functions, they form a very nice barrier to control the integral curves. So the function S here, it more or less tells you, right, like how far is the principal orbit is away from being umbilical, right? But to me personally, I think the function S is a little bit not natural, but it's useful, right? And the function T more or less tells you the initial condition, right? How large the F2 should be, which is the size of the singular orbit. And the function P, it just comes from the derivatives of the function capital S. Right, so by taking derivatives of these functions, right, we have, all these complicated formula. So as you can imagine, the derivative for the function P is very painful. Right? It took me quite a while to compute the formula. And the formula involves a polynomial that is called Q. And yet Q is another long formula, long polynomial. But if you can, like, more or less, right, the analysis shows that if we can tell the sign of the polynomial Q when P equals to 0 holds, then the algebraic surface P equals 0 will become a barrier for the phase space. right? So we would like to have the sign for the polynomial Q, right? But then the question kind of boils down to, studying the intersections of two algebraic surfaces, right? So recall that P is a algebraic surface, right? P equals to 0 is an algebraic surface, and Q equals to 0 is another algebraic surface. And there are three, the order is of 3. So the computation is kind of complicated, and you need computers to help you with that. So that's also my questions for all, for all you here. I'm not sure if you can have more beautiful arguments in algebraic geometry that can tell how the Q equals 0 and P equals 0 intersect. But anyway, right, like I said, we can focus on half of the phase space. So let the E plus to be the region where H is larger than 0, and also X1 is larger than X2. Right, so whatever is happening here, right, by the symmetry, you will have the same copies of E minus on the other end. Right, and then we further divide this set in two parts. So the first part is where the X2 is negative and P is less than 0. So we realize that no matter what D1, D2, and A's are, right, the quantities of A actually does not control how P equals 0 and P and Q equals 0 intersect. So they always separate in this yellow region over here. The only intersection will be the critical point P0. And we can further show that if the integral curves, right, admit x2 to be less than or equal to 0 initially, then it will enter this set where P is less than 0, and it will not converge to the P0 negative. Right? In other words, we shouldn't pay attention to integral curves that enter this region initially in order to get the heterocline. And what is more interesting is the region where H2 is larger than 0, right? And with P is less than 0. So in this particular region here, how large is the quantity A actually plays a role in here, right? We realize that if A is too large, then you can still argue that all the integral curves, that enter this region initially will have P less than 0 initially. And so that all these integral curves will not converge to P0 minus, right? So basically, P less than or equals 0 is a very bad news for the existence.
2 minutes late.
Yes.
2 minutes left.
Oh, okay. It's almost the end. Good. Yes. And yeah, lastly, we realize that, if we let the parameter to be 0, it will not converge. It will not go to P0 minus. And if we let A to be small enough, well, it turns out that the red triangle, the orange triangle region, right, you can actually allow P to be positive for some of the integral curves. So in that way, the integral curves will be in this blue triangular region initially for some parameters. And for integral curves in these regions, right, of course, they will still not converge to P0 minus. However, you can use the continuous argument to show that between the integral curves, that is in this blue triangular regions and 0, there will be some parameter that actually gives you the heterocline. So that's basically the ideas of the proof. So that sums up the my talk. So дякую за увагу. Thank you all.
Okay, thank you very much for this presentation, Professor Hanci Chi.